Hi, I'm Kate Tsuchiya from the University of Electrical Communications, Japan. At first, I'd like to thank all the committee members and volunteers who helped to make this conference. So let me start my presentation entitled An Optical Design for Avatar User Co-axial Viewpoint Telepresence. First of all, let me start with introducing our system easily. We designed a mid-eye imaging system for telepresence. It can capture an audience from the mid-air avatar's viewpoint. As background, a CG avatar is used for attractions such as Turtle Talk at several of the Disney theme parks and VR platforms such as hubs, Here, we can choose our appearance without any physical restrictions. I mean, we can change ourselves into any characters. This is an advantage of the CG avatar. In fact, some studies have shown that the avatar's appearance influences to the communication. However, this is only possible in VR space. We believe that the next step is to extend it to real space. Then, our purpose is realizing a communication through the CG avatar in real space. To do that, we propose a method taking the avatar from VR space to real space with the mid-air imaging technology. And next, I'll talk about the related work. There are three topics: mid-air imaging, telepresence system, and optical transfer of the camera viewpoint. At first, I'll introduce the mid-air imaging technology. There are various methods to display CG characters for the interactive system. One of that is displaying on screen. This method displays a CG character only on the screen. On the other hand, the media image is a real image formed in the air. So we can display the CG character in real space. To display the media image, we use an optical element called MMAPS, stand for micromirror array plates. Using this, the media image is displayed at a symmetrical position of the light source with respect to the MMAPS. So we use this element for our system. Second, I'll talk about telepresence system. Various types of telepresence system have been proposed. One of that is VR and AR-based systems such as Minimi. In this system, AR user can see the CG avatar using see-through HMD in real space, and VR user plays a role that avatar in VR space. So the users in VR space and real space can be connected, but the VR user still needs the VR space. Also, there are many systems using the robot. They realize real space interaction through the robot. Let me show you the comparison of telepresence systems in terms of the communication space and the avatar. In VR systems such as hubs, the users communicate in VR space through the CG avatar. In VR and AR-based systems such as Minimi, the communication spaces are VR and real space, and this uses the CG avatar. The robot system allows users to communicate in real space through the robot. Our proposed system uses a CG avatar like the VR or VR and AR-based system, and the communication space is real space like the robot-based system. Thirdly, I'll explain about the optical transfer of the camera viewpoint. There is a previous work that transfers the camera viewpoint using MMAPs. A mid-air camera means that transfers the camera, and it doesn't have a physical body, so it can go through a gap or mesh. A concave lens is also used for adjusting the focal point. Our system is based on this design. And next, I'll talk about the principle of our system. Here, I'll show you the optical design. Requirements of this system are displaying the midway image and transferring the camera viewpoint. Then it consists of a display, camera, concave lens, beam splitter, and MMAPs. The light from display is reflected with beam splitter, and that virtual image is D'. D' overlaps the camera. Then MMAPs forms the midway image with the light from D' and transfers the camera viewpoint to form the midway camera. And we implemented an experiment prototype. We used the DSLR camera and the mobile device as a display. Also, the transmittance of the beam splitter was 50%. Then, we conducted some experiments for the evaluation. We assume that the evaluation can be broadly divided into several parts. A basic part is applicability to telepresence. And the next step is evaluation of usability, like audio, visual, and so on. Then the final goal is productization. This time, we evaluated the applicability to telepresence. In this evaluation, we had two unknown parameters. The first is the effect of the MMAPs. This means how do MMAPs affect the capturing performance. The other is camera setting. This means what camera setting is appropriate for this system. At first, in evaluation 1, we confirmed that there are three effects of the MMAPs: stray light, brightness decay, and blur increase. Stray light means the light that does not form a midway image in an optical system using the MMAPs. It appears on the left and right of the midway image like this. This is also generated on the captured image in case of camera viewpoint transfer like this. In this area, the image cannot be captured properly. Then we conducted an experiment to evaluate brightness decay. In this experiment, we measured the luminance of the light source display and the midway image. It was measured by a luminance meter from several angles, 10 degrees to 60 degrees. And the display was placed in two patterns, horizontal and vertical. I'll show you the results. The horizontal axis is the angle and the vertical axis is the luminance ratio. In this system, the MMAPs are arranged at the angle of 45 degrees, so it is expected that the brightness is reduced to 40% or less. And next, we conducted an experiment to evaluate blur increase. In this experiment, we measured MTF that indicates the sharpness of the image. The edge image was displayed on a display, and it was photographed under two conditions, normal and MMAPs. Normal condition used the camera alone, and MMAPs condition used the transferred camera by MMAPs. Here is the results. The orange line is normal condition and the blue line is MMAPs condition. As you can see, the value of MMAPs is lower than the value of normal. This means the blur is increased by the MMAPs. To summarize evaluation 1, we confirmed that the MMAPs cause three effects. First one is blur increase, and second one is stray light. This affects the overall brightness ratio of the image. The third one is brightness decay. This can be solved by adjusting the camera setting. Based on their effect and evaluation 2, we will find design guidelines of our system. Alright, moving to the next part, I'll explain the evaluation 2. Here, we conducted face detection experiment to verify the camera setting. The purpose of this experiment is to find the appropriate camera setting for telepresence. We assume that users need a quality video to recognize the face to communicate each other. In preliminary experiment, we tried to use a face detection program. At this time, the face detector is not robust enough under the environment we tested, but humans are good enough to recognize the face in such an environment. So we assumed that if face detection works on the quality of the captured video, people can recognize faces and communicate using the same video. And we used that face detector for the evaluation too. Also, in preliminary experiment, alt ISO sensitivity setting didn't work. We guessed this is due to the brightness decay, one of the effects of the MMAPS. So we investigated the appropriate ISO sensitivity setting for face detection. In this experiment, we measured the face detection rate under two conditions, normal and proposed system. Proposed system condition used the MMAPS and the beam splitter. The participant was 1, and during the measurement, the participant moved her face and mouth like this video. And we measured the number of detection frames in 300 frames under 11 conditions of the ISO sensitivity. And I'll show you the results. The horizontal axis means ISO sensitivity, and EV stands for exposure value. And vertical axis means the detection rate. EV0 means an appropriate exposure under normal condition. In the case of this setting, detection rate is maximum under normal condition. As for proposed system condition, there are 3 settings that exceed the maximum of normal condition. There are settings of 4 to 16 times the appropriate exposure. This means they are appropriate settings. From 2 evaluations, we found 3 design guidelines. First, brightness decay can be solved by adjusting the ISO sensitivity. The adjustment is to set the ISO sensitivity to 4 to 16 times the appropriate exposure. Secondly, blur increase doesn't affect the face detection because in the face detection experiment, the maximum detection rate were comparable between the 2 conditions without any measures against blur. Thirdly, straight light reduces the effective angle of view. So this system is suitable for use in an environment where there is no subject on the left and right sides of the apparatus. Next, I'll introduce the application. The system design is shown in this figure. The positions of the camera and display were switched, and 2 motors were added to control the camera gaze direction. Also, the captured video is displayed on the HMD. The camera gaze direction is controlled based on the date that the HMD measures users' head movement. Then we implemented that. We used 2 compact cameras for stereoscopic view. And that gaze direction is controlled like this video. So the user can see the audience from avatar's viewpoint and also look around. We demonstrated this application at SIGGRAPH Asia 2019. At this time, we confirmed that users recognized audience's face. In conclusion, we showed 3 contributions. First one is that we designed an optical system superimposing the viewpoint of the avatar and the camera. Second one is that we evaluated the applicability to telepresence. And the result shows that it can be applied for telepresence, and we also found design guidelines. Third one is that we implemented an application for telepresence. This is all for my presentation. Thank you for your attention.